Hello, you are welcome once again to our lesson, Chemistry 235, Basic Organic Chemistry. Today, we continue with our discussion on the stereochemistry of organic compounds. Previously, in our last lesson, we started discussing stereochemistry. Today, we continue. And as usual, I'm your tutor, Mubarak Amin. Today, at the end of today's class, you should be able to define optical rotation. You should be able to identify dextrorotatory and levorotatory isomers. You should also be able to identify polarimeter. You should be able to calculate the specific rotation of a compound given the relevant experimental data. You should also be able to define racemic mixture. You should be able to define and explain the lack of optical activity of racemic mixture. In addition, you'll be able to define and determine optical purity. You should be able to determine percent composition of an enantiomeric mixture from polarimetry data and from specific rotation formula. You should also be able to define, discuss, and identify geometrical isomers. You should be able to draw structural formulas that distinguish between cis and trans molecules, as well as designate geometric isomers as E or Z isomers. These terminologies are the key terms you'll be encountering while the lecture progress. In our previous lecture, we talked about stereoisomers as isomers in which the atoms are connected in the same way, but they differ in spatial arrangement, the way they are arranged in space. And we mentioned that optical isomers are isomers that contain chirality centers. And a chirality center is a carbon atom that is bonded to 4 different other atoms or group of atoms. Chirality center is also referred to as stereogenic center, stereocenter, or asymmetric carbon, as depicted in this diagram. The dotted red, the red letter here is a chirality center. Similarly, the blue dot here is also another chirality center. A compound containing a chirality center can exist as 2 different isomers. We learned this previously. The 2 isomers are non-superimposable and are referred to as enantiomers. In other words, enantiomers are non-superimposable isomers that are mirror images. A compound or a molecule containing a chirality center is also a chiral compound or a chiral molecule, provided it does not contain a plane of symmetry. Now, optical rotation. This is a new terminology. Optical rotation, a new topic. Optical rotation is a phenomenon observed when a molecule rotates the plane of polarization. So when a molecule rotates the plane of polarization, we said the molecule is optically active, and the phenomenon is known as optical rotation. Enantiomers, they are the same in all respects. Physically, that is, they have the same boiling points, the same melting point, the same solubilities. They also have the same chemical properties. They react with a chiral molecule in the same way. The only difference to those properties depends on group bonded to chirality center or the way they are arranged in space. One of such properties that make a difference is the way they interact with polarized light. In other words, enantiomers interact with polarized light in different ways. Polarized light is light that is reflected or transmitted through certain media so that all vibrations are restricted to a single plane. Compounds containing chirality center, in other words, chiral compound, rotates the plane of polarization. Such compounds that rotate the plane of polarization are said to be optically active. Compounds that do not contain chirality center are known as achiral compound, and they do not rotate the plane of polarization. Thus, they are optically inactive. A chiral compound rotates the plane of polarization in either clockwise or a counterclockwise direction. If one enantiomer rotates the plane of polarization in a clockwise direction, its mirror image will rotate the plane of polarization exactly in the same amount in a counterclockwise direction. You need to take note of this point carefully, that if one enantiomer rotates the plane of polarization in a clockwise direction, its mirror image, that means its enantiomer, will rotate the plane of polarization exactly the same amount in the counterclockwise direction. In other words, in the opposite direction. An optically active compound that rotates the plane of polarization in a clockwise direction is called stereorotatory. The one that rotates in the clockwise direction is said to be stereorotatory, and it is indicated by a plus sign. The symbol for it is plus. In other words, symbol for stereorotatory is a positive sign. On the other hand, an optically active compound that rotates the plane of polarization in a counterclockwise direction is said to be levorotatory. Okay, the enantiomer that rotates in a counterclockwise or anti-clockwise direction is said to be levorotatory, and it is indicated by a negative sign. Destro and levo are Latin prefix for to the right and to the left, respectively. And this is a typical example. We have alanine, L-alanine, and D-alanine. Whereas D-alanine is levorotatory, L-alanine is destrorotatory. And L-alanine is S enantiomer, D-alanine is the R enantiomer. You need to take note and note carefully that levorotatory and dextrorotatory are symbols indicating the direction in which an optically active compound rotates plane of polarized light. Whereas R and S indicate the arrangement of the group about a chirality center. Therefore, destrorotatory, levorotatory, and R and S are not synonymous. They are not synonymous. A compound can be destrorotatory and have the S configuration, as we have seen in the previous example. Here, the L-alanine is a destro enantiomer, and yet it has the S configuration. Whereas D-alanine is the levo enantiomer, it has the R configuration. So being destrorotatory does not mean it must be R, and being levorotatory does not mean it must be S. A compound may have the R configuration and be destrorotatory. Some compounds with the R configuration are destro, while some are levo. There is no relationship between RS and the direction of optical rotation. For example, if you take 2-butanol, S2-butanol, okay, is destro. Destro rotatory as pure liquid can refer to the same molecule as plus 2-butanol and vice versa. Sign of optical rotation can sometimes change based on the solvent concentration and other factors. Polarimeter. A polarimeter is an instrument that is used to measure the amount that an optically active compound rotates the plane of polarized light. And this is a schematic diagram representing a polarimeter. We have the source of the light, the polarizer, the sample, and the analyzer, then the detector. And here on the left is a polarimeter. This is what a polarimeter looks like. Where this is a schematic diagram representing polarimeter. A polarimeter, again, is an instrument used to determine the angle through which plane polarized light has been rotated by a given sample. An analyzer is the component of polarimeter that allows the angle of rotation of plane polarized light to be determined. Specific rotation. The specific rotation of a compound is the number of degree of rotation caused by a solution of 1.0 gram of the compound per mil of solution in a sample tube 1.0 dm long, decimeter long at specified temperature and wavelength. This definition can also be transformed into a formula as you have here. Specific rotation can be calculated from this formula. This symbol here represents specific rotation, while you have alpha observed rotation divided by length of the sample tube and concentration of the solution in gram per mil, where alpha is the specific rotation. Alpha is square bracket, specific rotation. T is the temperature. Lambda is the wavelength of the incident light. Alpha that is not in bracket is the observed rotation. L is the length of sample tube in decimeters. And C is the concentration of the sample in grams per milliliter of solution. Specific rotation are normally measured at 20 degrees Celsius, and this property may be indicated by the symbol alpha 20D. Sometimes the solvent is specified in parentheses behind the specific rotation value. For example, if you have this notation, alpha 20D means the specific rotation is at 20 degrees, and in sodium line, D is equal to plus 12 in chloroform. The solution for the measurement was in chloroform. These are examples of how to calculate specific rotation. We have this question. The observed rotation of a 2.0 gram of a compound in 10 ml of solution in a polarimeter tube 25 centimeter long is plus 134 degree. What is the specific rotation of the compound? So this is how we solve this problem. The observed rotation that we are given is plus 134 degree. The length of the sample tube is given as 25 centimeter. Now, to calculate specific rotation, we have to convert this 25 centimeter to decimeter. Thereby, we divide by 10. 25 divided by 10 decimeter. And this gives us 2.5 decimeter. The concentration, again, should be in grams per mil. We are given that we have 2.0 gram in 10 mil. So we divide 2.0 divided by 10 mil. That gives us 0.2 gram per mil. Therefore, specific rotation now will be observed rotation divided by length times concentration, which is plus 134 degree divided by 2.5 times 0.2. And this gives us 268 degrees Celsius. That means the specific rotation of the sample is plus 268 degrees. You can have this question as exercise to practice. A sample with a concentration of 0.3 gram per mil was placed in a cell with a length of 5 centimeters. The resulting rotation of this at the sodium D line was plus 1.52. What is the specific rotation of the sample? I will leave this question for you to practice. Now, Rzenik mixture. Rzenik mixture. A mixture of equal amount of a pair of enantiomers is called a racemic mixture, a racemic modification, or a race mate. In other words, if you have equal amount of enantiomers, the dextro enantiomer and the levo enantiomer, you have equal amount of them in a sample. That equal amount is known as racemic mixture. Another terminology for racemic mixture is racemic modification or a race mate. Racemic mixture are optically inactive and are indicated by a plus minus sign. Wherever you see this type of sign in front of the compound, you know that definitely you have a racemic mixture. An example here is if you have plus minus 2-bromobutane contains plus and minus enantiomers in equal amounts. In other words, 50-50 amounts. You can also use this simple question and practice. We have S plus monosodium glutamate, shortened as MSG, is a flavor enhancer used in many foods. It has a specific rotation of plus 24 degrees, and this is the structure of MSG, monosodium glutamate. Now, you have to answer this question. What is the specific rotation of R minus monosodium glutamate? What is the specific rotation of a racemic mixture of monosodium glutamate? I will leave this question for you to be thinking about it and answer. Optical purity. Optical purity. Optical purity or enantiomeric excess. Another terminology for optical purity is enantiomeric excess. This is the ratio of the observed specific rotation of a compound to the specific rotation of the pure enantiomer of that compound. Okay, in the situation you have enantiomers, we said that an equal amount of enantiomers is a racemic mixture. In the situation you have enantiomers, a mixture of enantiomer which are unequal. They are not racemic mixture, they are unequal. Okay, there will be a specific rotation for that mixture, which will be different from the pure enantiomer. So the ratio of the mixture to the pure is what we refer to as optical purity. From optical purity, we can determine how much of enantiomer is present in a sample. The optical purity is a comparison of the optical rotation of a pure sample of unknown stereochemistry versus the optical rotation of a sample of pure enantiomer. And most of the time, optical purity is expressed as a percentage. An enantiomerically pure sample means there is one enantiomer present. If a sample of an optically active compound has an observed specific rotation of 0, then the sample contains a racemic mixture. Because the rotation in the racemic mixture, the rotation of dextro will cancel out the rotation of the level. As a result, the net specific rotation will be 0. If the sample only rotates the plane of polarized light half as much as expected, then the optical purity is 50%. That means the mixture is 50% pure. That's what it means. If, however, the observed specific rotation deviates from the value of a pure enantiomer, then the sample contains a mixture of the enantiomer in an unequal proportion. Optical purity or enantiomeric excess can be determined mathematically as this. Percentage optical purity is given as specific rotation of a mixture divided by specific rotation of pure enantiomer multiplied by 100. From this formula, we can be able to determine percentage optical purity. Because R and S enantiomer have equal but opposite optical activity, it naturally follows that a 50-50 racemic mixture of two enantiomers will have no observable optical purity. Okay, if we know the specific rotation for a chiral molecule, we can easily calculate the ratio of enantiomers present in a mixture of two enantiomers based on its measured optical activity. When a mixture contains more of one enantiomer than the other, chemists often use the concept of enantiomeric excess to quantify the difference. Enantiomeric excess can be expressed as percentage more abundant enantiomer minus 50 times 100 divided by 50. This will give us enantiomeric excess. For example, a mixture containing 60% R enantiomer and 40% S enantiomer will have a 20% enantiomeric excess. That is 60 minus 50 times 100 divided by 50. We give us 20%. The specific rotation. Okay, this is an exercise for you to practice again. You can, let me give you this question as an assignment that will be submitted. You will submit it in a Word format and send to my email. This assignment, these questions, these 3 questions are assignment for you. The specific rotation of S carbon is plus 61 degrees. The optical rotation of a sample of a mixture of R and S carbon is measured as minus 23 degrees. Which enantiomer is in excess and what is its enantiomeric excess? What are the percentage of R and S carbon in the sample? 2. The specific rotation of S plus 2-bromobutane is plus 23.1 degrees. A sample of 2-bromobutane has an observed specific rotation of plus 9.2 degrees. What is its optical purity? A mixture contains 3 grams of plus 2-bromobutane and 2 grams of minus 2-bromobutane. What is the rotation of the mixture? Given that plus 2-bromobutane has a specific rotation of 23 plus 23.1 degrees. So you can answer this question and submit later on. Now, with that, we have rest our case for the meantime on enantiomers. You remember when we were discussing the type of isomers, we said isomers have 2 types. We have the constitutional isomer, we have the stereoisomers. The stereoisomers have some division, the conformation isomer and the configuration isomer. And the configuration also has 2 types. We have the enantiomers and the geometrical isomers. All along, we have been discussing enantiomers. Now, we want to discuss geometrical isomers. I hope you recall this concept. Geometrical isomerism is a phenomenon in which 2 compounds possess the same structural formula but differs in spatial arrangement of the group around the double bond. Take note of that. Double bond is very important. Geometrical isomers results from restricted rotation about carbon-carbon double bond. Restricted rotation can be caused either by double bond or by a cyclic structure. For example, 1,2-dichloroethane, maleic and fumaric acid, and so on and so forth. Here we have 1-bromo 3-chlorocyclobutane. 1-bromo, this is a cyclic structure, cyclic compound. And this structure, as you have it here, you can see that bromine and chlorine are on the same side. So this is 6-1-bromo 3-chlorocyclobutane, and this is the trans isomer. These are geometrical isomers. Here's another one, 1,4-dimethyl-cyclohexane. You can see here that the methyl group are on the same side. Here they are on the opposite side. This is the cis isomer, and this is the trans isomer. And here you have 1,2-dichloroethene. 1,2-dichloroethene. This is you can hear chlorine, the chlorine atom are on opposite side. This is the trans isomer. Here they are on the same side. This is the cis isomer. Then you have maleic acid and fumaric acid. Here, this is fumaric acid. This is maleic acid. In maleic acid, the carboxylic acid group are on the same side of the double bond. The cis, that's why it is maleic acid. The trans isomer, the carboxylic acid are on opposite side. The isomer with similar group on the same side is known as the cis isomer. while that with similar group on opposite sides is known as the trans isomer. Thus, geometrical isomer are also known as the cis trans isomer. Then you have these simple exercises for your practice. Draw the cis and trans isomers for the following compounds: 1-ethyl, 2,3-methyl cyclobutane, 1-bromo, 4-chloro-cyclohexane, 2-methyl 3-heptene, 1,3-dibromo-cyclobutane. Then you have this: which of the following compounds can exist as cis-trans isomers? For those compounds, draw and label the cis and trans isomers. And you have this compound. Which one of them can exist as cis and trans? And for the one that can exist as cis and trans, draw the cis and trans isomer. Cis-trans isomerism also occur in cyclic compound. We have seen an example of this. In ring structures, groups are unable to rotate about any of the ring carbon-carbon bonds. Therefore, groups can be either on the same side of the ring, which is cis, or on the opposite side of the ring, which is trans. For our purpose, here we represent all cycloalkanes as planar structures, and we indicate the position of the groups either above or below the plane of the ring. As we have here, this is 1,2-dimethyl cyclopropane. Here, the methyl group are on the same side of the ring. So this is the cis isomer. Here, they are on opposite side, 1,2-dimethyl cyclopropane. This is the trans isomer. Here are other examples. Cis 1,3-dimethyl cyclobutane. This is trans 5-bromo, 1,4-cis-trimethyl, 1,3-cycloheptadiene. 1,3-cycloheptadiene. Then you have this one, trans 2,4-dichloro, 1,1-dimethyl cyclohexane. Then you have this one, cis 3,5-diphenyl cyclopentene. 3,5-diphenyl cyclopentene. Then you have these outward structure of cyclohexane, also depicting trans and cis isomer. Now, the EZ system of designating geometric isomers. EZ of designating geometric isomers. As long as each of the carbons of an alkene is bonded to only one substituent, we can use the term cis and trans to designate the structure of the alkene. If the hydrogen are on the same side of the double bond, it is the cis isomer. If they are on opposite sides of the double bond, it is the trans isomer. If the alkene is tri or tetra substituted, the use of cis and trans becomes meaningless. Okay? Since we do not know which two of the three are being described, which two of the three groups are being described. For example, if you take 3-methyl 3-heptene, 3-methyl 3-heptene, and look at the carbon-carbon double bond and the groups around the double bond. Here you have methyl, you have ethyl, and you have propyl. So which of these is cis to which one? It is difficult or not easy to designate any of the isomer of these as cis or trans. Also, if you examine this one, 3-bromo-butyenoic acid. 3-bromo-butyenoic acid. You have carboxylic acid, bromine, and methyl around the carbon-carbon double bond. So which of these two we say is cis? Which one will be trans? Because of this situation, the EZ nomenclature was designed. If you have a carbon-carbon double bond with a methyl group and a bromine on one carbon and an ethyl on the other, it is neither trans nor cis, since it is not clear whether the ethyl group is trans to the bromine or to the methyl. This is addressed with a more advanced EZ nomenclature. EZ nomenclature. The IUPAC system for naming alkene isomers, called the EZ system, is based on the same priority rules as RS system, which allow you to rank any groups. In other words, we borrow a leaf from the designating enantiomer as S or R. Okay, we borrow ranking the group around the double bond. The priority rules are often called the can in gold prelog. The rule works as follows. This is a recapitulator. Each carbon in the pi bond is attached to two substituents. For each carbon, these two substituents are ranked 1 or 2, according to the atomic number of the atomic directly attached to the carbon. For example, chlorine is greater than fluorine, using the can in gold prelog priority rules. If both substituents ranked 1 are on the same side of the pi bond, the bond is given the descriptor Z. If they are on the same side, it is Z. This Z, short for German zusammen, is from the word zusammen, which means together in German. If both substituents ranked 1 are on opposite sides of the pi bond, the bond is given the descriptor E, which is short for German Entgegen, which means opposite. Okay, this is a typical example. This is carbon-carbon double bond. Then you have the groups around the double bond. We now rank these groups on this carbon atom. We rank the one with higher priority will be 1, the one with low priority will be 2. We also do the same thing for this carbon atom. We rank the one with the higher priority will be 1, the one with the low priority will be 2. Now, in this particular case, the one with higher priority, they are on the same side. Therefore, this one is the Z isomer. And in this case, they are on opposite sides. So this is the E isomer. So this will solve the problem of not being able to designate an isomer as cis or trans. This is what we just described, that you rank. These are a typical example now. We consider this carbon, this is another carbon, this carbon here. What the groups that are bonded to this carbon is bromine and fluorine. Because bromine has higher atomic number than fluorine, bromine is rank highest priority 1 and fluorine 2. Now, considering this other carbon atom, you have chlorine, you have methyl. In methyl, carbon is one that is directly bonded to the carbon. Because chlorine has higher atomic number than carbon, chlorine is rank 1, higher priority, while carbon is rank 2. Now, in this case, the one that is ranked with high priority are on the same side. Here, they are on opposite side. So this one that they are on the same side will be the Z isomer. Here, the opposite side will be the E isomer. The Z isomer. Okay, because the higher priority are on the same side. And E isomer because they are on opposite side. You can use this mnemonic also to remember this Z Zen Zeit. You can use this that will help you to always remember that Z mean the same side or Z mean the same side. In the situation you have a tie, we also break the tie just as we do for enantiomers. For instance, in the alkane below, one of the carbons of the alkane is attached to 2 carbon atoms. How do you determine priority? You also walk to the next bonded atom. Here, if you consider this carbon atom, you have bromine, you have ethyl. You know that here carbon is bonded to this carbon, and here you have bromine. Bromine has higher atomic number than carbon. So bromine, you have the higher priority, 1. Then here you have carbon, 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 carbon. Also you have carbon, carbon. So for you to determine the priority or to break the tie here, this is carbon, this is carbon. This carbon is bonded to 2 hydrogen atoms and another carbon atom. This carbon is also bonded to 2 hydrogen atoms and another carbon atom. This other carbon atom here is bonded to 2 other carbon atoms, while this carbon atom here is bonded to hydroxy. Okay, we are working outward to break the tie. Here, this one is bonded to 2 hydrogen atoms and 1 carbon atom. This one is bonded to 2 hydrogen atoms and 1 carbon atom. The carbon atom here is bonded to 2 carbon atom and 2 carbon atom, yes, and 1 hydrogen. While the carbon here is bonded to 2 hydrogen atom and oxygen. Now, because this one is bonded to oxygen, this one is bonded to carbon. Oxygen has higher atomic number than carbon. It will confer the higher priority to this site. If the two substances bonded to an sp2 carbon start with the same atom, there is a tie. You must move outward from the point of attachment and consider the atomic number of the atoms that are attached to the tied atoms. So what we are I've just explained briefly is what has been spread out here. That here you have carbon, hydrogen, hydrogen. Here you also have carbon, hydrogen, hydrogen. Then you move to the next carbon. Here you have oxygen, hydrogen, hydrogen. And here you have carbon, carbon, hydrogen. Okay? To the next atom. Then when you come here, you notice that here you have oxygen, here you have carbon. Oxygen has higher atomic number than carbon. That is why this one will be 1. So here, the one that is ranked higher priority, they're on the same side. So this will be the Z configuration, the Z isomer. You can also use this exercise as practice. Designate each of these compounds or draw and label the E and Z isomers for each of these compounds. The E and Z isomers for each of these compounds as your exercise. Here is some other exercise. We have this name here, Z 3-methyl 2-phenyl X2-ene. Draw the structure. Then you have this structure, write the name. This is what this means. Here's another exercise for you to practice. 3 alkenes are shown below. Which one can be described using cis-trans notation? Which of these can be described using cis-trans? Now, can we convert cis-trans to EZ? Is it possible that when you have identified an isomer as cis or as trans, can we immediately say cis is cis or trans is E? For example, if you have 2-dichloroethene and butyene, this is 1,2-dichloroethene. This is trans, for this case, is E, because here you have chlorine and chlorine, which are ranked high on opposite side. So this is trans, this is E. Here also, you have cis and Z because the chlorine are on the same side. Is this always true that trans is equal to E and cis is equal to Z? Is it always true? We shall see very soon. Here is 2-butene, 2-butene, methyl group, they are on the same side, cis, Z. Here the methyl group are on the opposite side, trans, E. Okay? It doesn't always work like that. Translating cis and trans to Z and E does not always work. For example, if you consider this, this compound. This is clearly a cis isomer because the methyl group are on the same side. It has two methyl groups on the same side of the double bond. But work out the priorities on the right hand end of the double bond. On the right hand, we have methyl, we have hydrogen. This is carbon, this is hydrogen. Carbon will rank higher, this is 1. Hydrogen will rank 2. Then we go to the other end, methyl, bromine. Bromine will be 1, methyl will be 2. So in this case, 1, 1, they are on opposite sides. So this is cis, but it is E, not Z. That means that the two higher priority groups are on opposite sides of the double bond. And so this is an E isomer and not a Z. So you should never assume that you can convert directly from one of this system into the other. It does not always work. You have to work it out. The only safe thing to do is to start from scratch in each case. It doesn't matter that the two systems will sometimes give different results. The purpose of both systems is to enable you to decode a name and write a correct formula. Properly used, both systems will do this for you, although the cis-trans system will only work for straightforward molecules. The cis-trans system does not work for all the molecules, but the EZ will work for all molecules. Now, in summary, or as a recap of what we have been discussing all along, an optically active compound that rotates the plane of polarization in a clockwise direction is called the stereorotatory and is dictated by a positive sign. On the other hand, an optically active compound that rotates the plane of polarization in a counterclockwise direction is said to be levorotatory and is indicated by a negative sign. Destro is not always the same as S, and levo is not always the same as R, and vice versa. A polarimeter is an instrument that is used to measure the amount that an optically active compound rotates the plane of polarized light. The specific rotation of a compound is the number of degree of rotation caused by a solution of 1.0 gram of the compound per mil of solution in a sample tube of 1.0 decimeter long at a specified temperature and wavelength. A mixture of equal amount of a pair of enantiomer is called a racemic mixture, a racemic modification, or a racemate. Excuse me. A racemic mixture are optically inactive and are indicated by a plus minus. Optical purity or enantiomeric excess is the ratio of the observed specific rotation of a compound to the specific rotation of the pure enantiomer of that compound. Geometrical isomerism is a phenomenon in which two compounds possess the same structural formula but differ in spatial arrangement of the group around the double bond. Geometric isomers result from restricted rotation. Restricted rotation can be caused by either a double bond or a cyclic structure. The isomer with similar group on the same side is known as the cis isomer, while that with similar group on opposite side is the trans isomer. Cis transisomerism also occurs in cyclic compounds. In ring structures, groups are unable to rotate about end of the ring carbon-carbon bond. Groups can be either on the same side of the ring, cis, or on the opposite side of the ring, trans. If the alkene is tri or tetra substituted, the use of cis and trans becomes meaningless. However, this is addressed with a more advanced EZ nomenclature. For EZ nomenclature, each carbon in the pi bond is attached to two substrates. For each carbon, these two substrates are ranked 1 or 2, according to the atomic number of the atom directly attached to the carbon. If both substrates rank 1 are on the same side of the pi bond, the bond is given the descriptor Z, which stands for Zuzami, meaning together. If both substrates ranked 1 are on opposite side of the pi bond, the bond is given the compound is given the descriptor E, short for Erzgegen, the German Erzgegen, meaning opposite. Cis is not always the same as Z, and trans is not always the same as E, and vice versa. You can consult these resources for further reading. If you need to read more, you can either of these resources, further Yokanis Bruce, KS Tewari, or any of the website address. You can read more about this topic. This is part 2 of our series, in the series of stereochemistry of organic compounds. In the next class, we shall be discussing the concluding parts. I thank you for your attention. See you. I will be seeing you